Hello, ladies and gentlemen. We are here to present our project for embedded system, real-time audio processing. My name is Shen Huizhi, and here is my partner.
My name is Tong. Hey, what's wrong with my voice? It sounds weird.
Relax, it's just a pitch shifting effect. Let me get your voice back. Now you can try.
Let me see. It's much better now. Thank you. Let's continue our presentation.
Okay, so this first diagram here shows the power spectrogram. The x-axis shows time, y-axis shows frequency, and the color indicates the power strength. Purple means weak power, and red means strong power.
And we can see here we set the frequency range at 500 Hz. You can adjust it according to your needs. Let's say we change the maximum value to 300 Hz. Then we can see the change in the y-axis in the diagram.
The next two graphs here shows the waveform of the original speech and the pitch-shifted speech. We can adjust the pitch here.
And you can adjust your voice to higher pitches. Then you'll sound like this. And you can also change it to lower. And you sound another way. You sound like a monster.
That's funny. Besides, we also implement pitch comparison system to compare your voice pitch and the pitch of a sound. You can find your singing accuracy by pitch comparison.
Yes, you can. Let's turn up the volume for the song selected. You can see in the graph we implemented both the figure for song and for your voice. The yellow line stands for your voice, and the red line stands for the song.
In this project, we have 3 levels of difficulty. In the easy mode, if your singing is accurate, if the difference between your voice pitch and the sound pitch is less than 30 Hz. And then the threshold level is 20 Hz and 10 Hz for hard level. Our singing is great.
Are you joking?
Really?
Oh, let's take a closer look at the project.
Okay.
Okay. Here in this project, we use MIDAC to process the data. The audio input is connected to this microphone, and the audio output is connected to a loudspeaker. Our first task is to detect the spectrogram of the input. In doing this, we first apply a short time Fourier transform on the input signal. This is realized by employing an element called STFT provided by LabVIEW. The processed data is then passed to the configured spectrogram indicator. The output of the configured spectrogram is then passed to the graph in the user interface so the user can read it from the graph. The x-axis of the graph is time. The y-axis is the frequency. There is also a z-axis indicates the power of the spectrogram. We can see that the power varies with time. The range of the maximum and minimum frequency can be set by the user through the property node of the y-axis, which is here. We can see we can set these two. Now we can take another look at how do we realize the pitch shifting. In the pitch shifting part, first of all, we need to divide the signal into blocks using these elements provided. These blocks are then passed to the Gabor transform. In the Gabor transform, each signal block is represented by Gabor coefficients in the time-frequency domain using the Gabor transform. Also, here we use a time window designed by us, which is called the dual time window. We can see the timestamp and the frequency bins properties are set here. Then we use a phase vocoder to stretch the signal in the time domain. After that, the signal is passed to the Gabor extension, and then passed to another to this element, which applies a resample. So the signal is back to the time domain with the same time duration. So we can use that in the user interface, and we can output the audio.
The output signal of the pitch shifting system is sent to MyDep as output, and another part is sent to the pitch detection system to measure the pitch. So we will first perform fast Fourier transform on the signal and measure the magnitude in time frequency domain. Then we find the frequency with the maximum power for each time instance. This frequency is the so-called pitch at that particular time. Next, we will have our sound and voice pitch comparison system to find the accuracy of singing. This system is implemented in a separate loop here. So first, we need to choose our existing sound of wave format from a laptop. The program will read the sound file information such as file format and sample numbers, and configure the sound output channel using the same specifications as input. The sound system will read 2,200 samples in one loop and filter them with the normal human voice range, so that only the pitch of singing will be detected. Similar as voice pitch detecting, we determine the maximum frequency components for each subset of some samples. Then we use the average value of 3 sets of frequency as pitch. The detected pitch of some is then passed to voice signal for comparison. So in the pitch comparison system, the output of this the voice pitch will wait for the sound pitch first, and then these two pitches graph are plotted in the same diagram here. So the user can select a sound level of difficulty from easy, medium, and hard modes. In easy mode, for example, we define the threshold at 30 Hz. If the difference, we compare this with voice pitch. If the difference of voice pitch and sound pitch is less than 30 Hz, we say there's a match and the match light is on. Otherwise, the light is off. The threshold for media level is 20 Hz and hard level is 10 Hz.
In summary, this program can show the spectrogram and the pitch of the input signal.
Yes, it can also perform pitch shifting and pitch comparison of voice and sound.
Okay, that's the end of our presentation. Let's enjoy our result of our hard work.
Boom,
Boom, boom, boom, boom, boom,
boom, boom, boom,
boom, boom, boom, boom, boom, boom, boom.